let's have a look at induction. So basically the procedure we go through, I mean, you don't have to write down step 1, step 2. Mind you, it's funny to see how many people do. Basically, the first step is you go and prove it for usually n equals 1, but whatever the first case is. I mean, you might be trying to prove something for even numbers. In that case, the first case would be n equals 2. Whatever the first case is. Then you go, all right, well, look, I'm going to assume what it is that I'm trying to prove. I'm going to assume this is actually correct. And then using that assumption, I'll go and prove it's true for the next case. And then if I can prove that, because back in step 1, I proved it true for the first case, then I can say, yes, well, they're all blue. Because if it's true for the first case, and then it's true for n equals k plus 1, but when you do your proof, this is the crucial part of the proof. Once you've done your proof, you conclude it and saying, well, what I've actually now just done is I've proven the result is true for n equals k plus 1 if it is true for n equals k. Because my proof relies on my assumption being correct. And I assumed it was true for n equals k. Now, if it's not true for n equals k, then my proof is a whole piece of garbage. Because that's what my proof hinges on. And that's when I go back to the first case and say, well, hang on a sec, I just proved it was true for n equals 1. So if it's true for 1, it must be true for 1 plus 1. Because we just said, if it's true for k, it's true for k plus 1. So if it's true for 1, it's true for 1 plus 1. Oh, I now know it's true for 2. Oh, well, if it's true for 2, it must be true for 2 plus 1. Oh, it's true for 3. And if it's true for 3, and so on and so on. So you've induced that it's true for all integers. So that's the difference to the deduction of a proof, because deduction starts with known facts, and we know we're working with things that are always true, and from that we deduce a proof. Here we're inducing. And it's really good for series. Okay, we have formulas for arithmetic series and geometric series, but they're just 2 series. We can have all sorts of series. This one here, the sum of odd numbers squared. And I'm being told that the formula for this is 1/3 n, 2n minus 1, 2n plus 1. So, okay, well, let's go and prove that that does indeed work. So say, step 1. No, you don't have to write step 1. Step 1, I'm going to prove it for the first case. Now, the first term, there's my general term there, 2n minus 1. So the first term turns out to be 1 squared. And I can see that from the pattern anyway. And 1 squared, of course, is 1. Using my formula on the right-hand side, if I sub n equals 1, yes, I also get 1. See, okay, it does work for the first case. So yeah, my left-hand side, right-hand side are equal. So hence, yes, it is true for n equals 1. I'm now going to assume what it is that I'm trying to prove. So I'm just basically going to change the n to a k. I just change the pronumeral. So n equals k, where k, in this case, is going to be some positive integer. And so that is what I'm going to assume. Again, essentially, it's the same as the question. I'm just using k instead of n. And then we're going to prove it true for k plus 1. It's always handy to write down what it is you're trying to prove. So now the last term will be 2k plus 1 all squared, and on the right hand side I'll have a third k plus 1, 2k plus 1, 2k plus 3. Okay, well these series type questions, to get the assumption in there, what I always do is I'll have my sum to k plus 1 terms, but I'll rewrite it as the sum to k plus the k plus 1 term, because the sum to k essentially was my assumption. And so I can replace all of these terms with the plus dot 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 with my assumption. We're assuming all of that is a third k, 2k minus 1, 2k plus 1, plus 2k plus 1 squared. And we have to now go and prove that's the expression we wrote down. Now a mere mortal would expand this whole thing out. I'm not going to do that, of course. Keep an eye on what it is you're trying to prove. Because eventually, I could expand the whole thing out, but eventually I'm going to have to factorise back in. Have a look at what the factors are. Now, if you look at the answer we're trying to get to, it has a factor of 2k plus 1 in it. And I can see straight away this has got a common factor of 2k plus 1. So I may as well factorise that out and make life easier for myself. So, there we go. I'm left with a third k, 2k minus 1, plus 2k plus 1. There's another factor. and that's a third. Now, it's not immediately obvious, but the 2k plus 1, if you think about it, is a third times 3. I notice my answer has to have a factor of a third. So I'm going to pull that out as well. So I pull out the third, and I'm now left with k, 2k minus 1, plus 3, 2k plus 1, which is just a quadratic. So this I will expand out, because that can be easy to factorise. Expand that out, so we get 2k squared plus 5k plus 3, which, yes, indeed, does factorise down to what we want, k plus 1, 2k plus 3. That's what I was trying to prove. So what have I done? Yeah, well, hence, I now know that it is true for k plus 1, but only if my assumption was correct. So only if it's true for k. Then comes our concluding statement where we tie it all together, and we say, well, hang on, I proved it was true for 1. I've just done my proof that it's true for k plus 1 if it's true for k. So tying that all together, I can say, well, since I know it's true for 1, then it's got to be true for all positive. I can induce every positive number from that. I think the real crucial part is this here. Right? You've proved it true for k plus 1. No, you haven't. You've proved it true for k plus 1 if your assumption was correct. And I think that's the crux of the inductive proof, that you mention that, hey, my proof is only as good as my assumption. My assumption works, beautiful, my proof works. Of course, they might put it in some notation saying it is a series. Now, personally, sometimes with some series, I prefer to write it out so I can get a feel for what all the terms are doing. I think it just gives me a better idea of what the pattern's doing. And notice I didn't write on a third, I wrote it as 1 on 1 times 3. So that's what these terms are doing. It's 1 over, and then I've got 2 consecutive odd numbers. So I get a feel for what the pattern is doing. Just like how I like to do it. So okay, prove it for 1, sub 1 in there, left-hand side. The first term in this is a third. Right-hand side, yes, that comes up with a third as well. So excellent. That works for n equals 1. So I'm now going to assume what it is I'm trying to prove. Now I've written it out as a series. Okay, we're going to prove for k plus 1. So the k plus 1th term, we're going to prove it's k plus 1 on 2k plus 3. So it's a series type. Again, I'll write it out as sum to k plus k plus the term k plus 1. But that's what I assumed. So let's substitute in my assumption. It's just simply k on 2k plus 1. Again, having a look at the answer. I want k plus 1 on 2k plus 3. So I want the denominator to be 2k plus 3. Well, algebraic fraction, I suppose I'll just do it like I normally would anyway and say, well, let's make the denominator the same and see what happens. All right, there's my fraction. It becomes k, 2k plus 3 plus 1, which on the top is 2k squared plus 3k plus 1. Now, this is where you can cheat and get away with it. Well, it's not cheating, it's fudging. But gosh, you never know what the top of this is going to factorise to be. Oh, k plus 1, 2k plus 1. Isn't that nice? The 2k plus 1s cancel. I mean, cancel the 2k plus 1s. Oh, look, there's our answer. So, all right, I now know it's true for k plus 1 if it's true for k. And so, well, I proved it was true for 1, so I can now induce it true for every positive integer. All right, I've picked some out of 6n. These ones are all series ones. Number 10's interesting because it's to do with a polygon. You sort of got to set that one out a little bit different. So I'll leave you to that one.